Hello viewers, welcome to Brilliant Online Academy. I would advise you that you always continue to subscribe to this channel because most of the times you will find that all that we discuss are examinable and they are very simple, and it enables the students of the understanding concept of these topics. Now in our today's lecture, we're going to discuss on the first principle of derivatives. And on the first principle of derivatives, your teacher today will be Teacher Shaban Obuya. Feel most welcome. Meanwhile, you can subscribe to our channel, like our videos, and actually just click on the notification button so that whenever we upload any video, YouTube will automatically notify you so as to get access to our learning resources. Welcome. So in the first principle of derivatives, the first principle of derivative, which is also known as the limit, the definition of limits, is written as the limit as h tends to 0 of function of x plus h minus function of x divided by h. So if you are asked to use the first principle of derivative, it is just more or less the same as the definition of limits, which is given by this. Now, to expand on this, I want us to use some of the examples that will guide us on how to apply this principle to find the derivatives of a function. Now, suppose you're given an example. We are asked to find the derivative of y is equals to 2 over root of x. Now, in simple terms, if it were not using the first principle, then this would be a little bit easier, because what you will do here, that is, if you are not now using the first principle, but we are using the power rule, what will we do? We'll have it like 2 over x raised to power half. So after having this, what do? You will factor out the numerator, which is also the constant. So if you factor out the constant, we'll have it to be 2 in bracket of 1 divided by x raised to power half. So after having this, what do? We write the reciprocal of this, and the reciprocal of this will be 2 into x raised to power negative half. So from this, we are able to differentiate this using power. So it will be 2 into negative of half x raised to power this minus 1, it will be negative 3 over 2. So if you open this bracket, it will be negative x raised to power negative 3 over 2. Write the reciprocal of this. This will be the same as negative 1 over x raised to power 3 over 2. And you shall have got the answer. But now, in our case, we are asked to use the first principle of derivatives. So it means we have to take our function and substitute it in our definition. And if we substitute it in our definition, this is what we will have. So we'll have the limit as h tends to 0 of 2 over root of x plus h and minus 2 root of x divided by h. Now, from here, we are going to multiply by the conjugate of the numerator. And for us to multiply by the conjugate of the numerator, we only change the sign in between the two functions. So this will be 2 root of x plus h, then plus 2 root of x. Then the denominator will also multiply by the same conjugate, x plus h, then plus 2 root of x. Now, let's open the brackets by multiplication. So if we multiply this times this, is just the same way as writing the limit as h tends to 0 of this squared, that is 2 over root of x plus h squared, minus root of, that is 2 over root of x squared. So you can expand it and see whether the all of this, if you multiply them, will still bring us to this point, over h times the conjugate, that is h into 2 over x plus h plus 2 root of x, everything multiplied by h. Now let's square everything on the numerator. If for us to square everything on the numerator, we'll have limit as h tends to 0 of 4 over x plus h minus 4 over x on our numerator divided by the all of this, that is h into 2 over root of x plus h plus 2 root of x. So if we have this, we first of all have to calculate the numerator. We have to calculate the numerator so that we have it under one LCM. So if we calculate this numerator, it will be the same as the LCM of x plus h and x will be x plus h times x. So x plus h goes there, x times 4 will be 4x minus x goes here, x plus h times 4 will be 4 into x plus h. Now from there, let's open this bracket. We have 4x minus 4x minus 4h divided by x plus h multiplied by x. So from here, 4x minus 4x will be 0. So we'll have negative 4h divided by the all of this. So we'll have our limit as h tends to 0 of negative 4h divided by x plus h multiplied by x. But remember that all of this is divided by h into 2 over root of x plus h plus 2 root of x. Okay, so let's rewrite this. And for us to rewrite this, it will be the limit as h tends to 0 of the all of these times the reciprocal of the denominator. So that will be negative 4h divided by 4, not 4 but x plus h multiplied by x times the reciprocal of that will be 1 over h into 2 raised to power x plus h, then plus 2 over root of x, Okay. Now this h will cancel h. So we'll have limit as h tends to 0 of negative 4 over x plus, wherever we have h now, we replace with 0. So we have here x times x will be x squared. So we have x squared multiplied by this. So this will have 2 divided by root of x plus 2 divided by root of x. So this will be the same as 2 of 2 root of x. So from here, let's now open this bracket. Let's open this bracket. So we have negative 4 divided by 2x squared times 2 root of x. So if we open this, if we further multiply this, we have negative 4 divided by 4x squared divided by x raised to power half, because 4 raised to power half is the same as square root of x. But if you have this, then that we have the same numerator, we have the same basis. What do we do? From laws of logarithms, when it is division, what do we do? We subtract the power. So we will subtract r from x squared. So we'll have negative 4 divided by 4x, but raised to power 2 minus half. So this will be the same as negative 4 divided by 4 times x raised to power 3 over 2. But 4 can go into 4. So we'll have our answer to be negative 1 over x raised to power 3 over 2. And if you look at this answer, it's more or less the same as the first one that we obtained. So by doing all this, you shall have proved the laws, the first principle of derivatives in deriving functions. Now, let us use another example. Still on the same, that is just applying the first principle of derivatives. Suppose we are asked to find the derivative of y is equals to x raised to power x. Now, in deriving this, it becomes much tiresome for us to derive this using the power. It is very simple to obtain this, the derivative of this using power, but that one will not earn you all the marks that are required. What do we do? In this section, we're going to apply the first principle of derivatives, or we're going to use the definition of limits to differentiate our function. Y is equals to x raised to power x. So let's replace our function in the definition and see what it will give us. So we have the limit as h tends to 0 of function of x plus h will be x plus h raised to power x, then minus x raised to power x divided by h. Now from here you will realize that we have a binomial expansion here. This, because we can't, there is no way we can differentiate this. So, but if we use binomial approach, then we are able to expand this. Then we subtract our function of x, function of y, which is x raised to power x. So let's rewrite this first. for us to rewrite this, we are going to expand it binomial. So it will be limit as h tends to 0. If we expand this binomially, it will be x combination from 0 multiplied by x combination 0 multiplied by x raised to power. Now we learn it is x combination 0, then x raised to power x, but y h will be raised to power 0. That is our first term. Then our second term will be plus x combination 1 x raised to power x minus 1, but now h will be raised to power 1 from 0 to 1. Then that is how it will go plus up to plus x combination x multiplied by x raised to power 0, but h now raised to power x. So that is, we have just expanded this binomial. Then you subtract our function itself minus x raised to power x, everything divided by h. Yup, we are together. So from here, what are we going to do? We are going to evaluate the whole of this and this. So if we have this, x combination 0 is 1. Any number to combination 0 is 1, and you can confirm that from your calculators. So x combination 0 will be 1. Then x raised to power x will just remain x raised to power x. Then h raised to power 0 will be 1. So any number raised to power 0 will be 1. So if we have 1 times x raised to power x, so we'll have the limit as h tends to 0 of x raised to power x plus, let's do this. For this, x combination 1 will be x. We know very well that any number combination 1 is just the same as that number, and you can confirm that from your calculators. So x combination 1 will be x multiplied by, this remains the way it is, that is x raised to power x minus 1. So we have x minus 1 x minus 1 then times h raised to power 1, then equal plus 2 x combination x, any number combination, that number is just 1. So we'll have 1 times x raised to power x. So we'll have h raised to power x, then minus x raised to power x. Everything divided by h. Now, from here, we can automatically do away with this, because this is positive x raised to power x, then we have negative x raised to power x. So this will go with this. So we'll have x multiplied by x raised to power x minus 1 times h raised to power 1 plus h raised to power x. So let's factor out the common value here, and the common value is h. So if we factor h from this numerator, we'll have the limit as h tends to 0 of h into x multiplied by x raised to power x minus 1 plus, then plus h raised to power, if we factor 1 here, it will be minus minus 1. So everything divided by h. Now this one becomes much simpler. This will cancel this. So we have our limit at h tends to 0 be equals to x multiplied by x raised to power x minus 1, then plus h, where we have 0, that is 0 now because h tends to 0, raised to power x minus 1, and this is automatically 0. So we have our answer for the limit as h tends to 0 of that function becomes x multiplied by x raised to power x minus 1. So this becomes our derivative using the first principle of derivative, and that is how simple it becomes. Now, to sum up, I want us to do one more example and see how simple this concept is. So, what if we are asked to apply the same definition to evaluate the derivative of this, that is f of x is given by x squared minus 4x. Now, so in real sense, without using the first principle, if we differentiate this, it will just be automatically 2x minus 4. So I want us to prove that using the definition, and this is our function. Now let's replace the function in our definition. It will be the limit as h tends to 0 of x plus h squared minus 4 into x plus h minus our function where it is, that is x squared minus 4x, but everything raised to power h. Now, after having done this, I want us to open this bracket, this alone first, so that we see when we open the whole of this bracket, then it will. So let's begin from this. So we'll have the limit as h tends to 0 of x squared plus 2xh plus h squared minus 4x minus 4h, everything in bracket, minus x squared minus 4x, but everything is divided by h. Now we open this bracket, so we have limit as h tends to 0 of x squared plus 2xh plus h squared minus 4x minus 4h. Now if we open this bracket, it will be minus x squared, but this will be positive, plus 4x, but everything here divided by h. Now let's see the like terms. If you look at this, we have positive x squared and negative x squared, so that cancels off. We also have negative x and positive x, so we have the limit as h tends to 0 of 2xh plus h squared minus 4h divided by h. Now we factor the common term of the numerator, so we have the limit as h tends to 0, then h into 2x plus h minus 4. Everything divided by h. So if we have this simple expression now, it is automatically that this will cancel this. So we have the limit as h tends to 0 be equals to 2x plus, remember h tends to 0, so we replace this by 0, then minus 4. So this will be simply the same as limit as h tends to 0 of 2x minus 4. And this becomes our derivative. And I think it's just the same way as when we use the direct approach. So guys, I hope this topic is now simplified and you are able to tackle any question that is related to the first principle of derivative to obtain the derivatives of functions. Thank you for watching this channel and you continue subscribing.